Hi, welcome to AWS Virtual Summit. I'm Shashank, and today I'll be talking about how you can get the most out of your deep learning projects when using your favorite deep learning frameworks such as TensorFlow, PyTorch, and MXNet. Here's how we'll spend the next 30 minutes or so. I'll start off with a quick refresher on machine learning and deep learning. After that, I'll introduce some of the key challenges we hear from our customers when they work on their deep learning projects. And through the rest of the presentation, we'll talk about how you can address these challenges. We'll talk about different considerations in deep learning, such as storage considerations, compute optimizations for CPUs and GPUs, networking optimizations, and also cluster management solutions. And we'll see a couple of demos as well. We'll see how you can use Amazon SageMaker to end-to-end optimize your stack to get the most out of your deep learning projects on AWS. I'll wrap everything with some summary and key takeaways, some resources for you to get started as soon as you finish watching this video. Machine learning is a data-driven modeling approach as opposed to previous techniques such as handwritten rules, where you would maybe say, if a customer bought product X, they may like product Y. These are handwritten rules, or in some cases, you may have first principles equations. Say you wanted to predict the trajectory of a satellite, there are equations for those. But for a lot of domains, you have to learn these rules directly from data, and this is where machine learning comes in. You provide your data, and an algorithm goes through your data set and comes up with models which can build predictive models for recommendations or forecasting and other such problems. And over the years, the research community has developed several hundreds of these algorithms, and they're specialized for different types of data sets and different domains. And one such subset of algorithms are called deep neural networks or deep learning. And these algorithms are very good for certain subsets of tasks, such as perception-based tasks in computer vision, in natural language processing, in text and speech analysis. And the idea is not new, and it builds upon classical neural network techniques and introduces new layers like convolutions and a lot more deeper layers and architectures. And in many cases, these have developed algorithms or models that can surpass human level accuracy in many domains, and has made solutions possible in domains which were previously considered unsolvable. So deep learning is obviously here to stay. What are some of the key challenges? Well, first, it's not just one algorithm. There are a host of different model architectures to choose from. And this can be challenging for a lot of not just new comers, but also veterans in the domain, because every problem is different. You have to choose from a variety of these listed model types here, or in many cases, author your own model type, depending on the specific problem that you're trying to solve. The second, of course, is deep learning is computationally expensive, and you need to be able to take advantage of CPUs and GPUs and powerful instances for distributed training, but also network and storage optimizations. And in many cases, you may not want to manage the infrastructure when doing large-scale training. And finally, the whole reason you train a model is to deploy it into production, which is why you may want to be able to deploy a highly secure, scalable endpoint in the cloud so your customers can access these models. But managing the infrastructure again and doing it at a reasonable cost and at high enough performance can be challenging. So let's go through each of these challenges and how you can address them using your favorite deep learning framework. Let's start off by talking about the ease of use approach. And deep learning frameworks are solving the ease of use and the approachability problem. And these frameworks actually provide you high-level abstractions to low-level linear algebra subroutines and other optimizations that are done on top of CPU and GPU instances. So you can focus on problem solving at the top and not focus on low-level optimizations. And TensorFlow, PyTorch, and MXNet are obviously the three most popular frameworks out there. And some of them even provide much more higher-level abstractions with Keras for TensorFlow and Gluon for MXNet that make it super simple for non-machine learning experts to just simply take a model and get started with their deep learning problem. And most of these frameworks also provide multiple interfaces for high level and low level if you really want to get deep, and you can scale them on a cluster. But what they don't provide you are cluster management solutions, and that is on you, the user, to figure out how to scale this on a cluster. They just provide the building blocks here. Now, deep learning is more than just a framework or more than just training and inference. There are a lot of upstream and downstream dependencies we'll talk about. And AWS is framework agnostic, so you can bring your favorite framework listed here or something else and run it on AWS to get the most out of AWS. So some of the downstream dependencies are, of course, compute optimizations. So you want your framework to be able to take advantage of CPU and GPU resources, multiple different types of GPU resources, networking optimizations, also storage optimizations with block storage and object storage and others. But even if your framework is fully optimized for these things, you still want to solve your problem end to end, because machine learning is more than just training and inference. So this is where machine learning services like Amazon SageMaker come into play, where you can develop your algorithms, manage experiments, debug your models, monitor your model endpoints, and basically have a fully managed service for training and inference at scale. So in order to get the most out of your deep learning framework, you want this full stack optimizations all the way from infrastructure services to machine learning level services, and with your favorite framework in between where you author your models. And when you combine all of these is how you can get the state-of-the-art performance with your models. And here's some benchmarks that AWS ran with Mask RCN, a popular computer vision model with 27 minutes to train. This is a record-setting benchmark. And also with BERT, a language model with 62 minutes to train. These are state-of-the-art results as of today. And you'll see in many cases that these are able to scale up to 192 GPUs with Mask RCN and 2048 GPUs with BERT. And you can do this with near linear scaling efficiency because of all these optimizations, not just the framework, but compute, storage, networking, and cluster management as well. And you can do this at reduced cost with support for managed spot instances training and also specific inference solutions such as AWS Inferentia and others we'll talk about. Okay, so let's take a look at some of the key optimizations that are available to you when you run your framework on AWS. So first is, of course, performance optimizations. And each of these frameworks include AWS optimizations, and we'll talk about how you can take advantage of them in subsequent slides. Let's say you want to train on a NVIDIA V100 GPU on a P3DN instance. It's one of the fastest GPUs available today in the cloud. Or you want to train these on G4 instances, the latest generation NVIDIA GPUs as well. These frameworks include optimizations for these frameworks, for these GPUs, so they are highly optimized for the CPU and GPU in that instance with the latest NVIDIA and Intel libraries, and they're fully qualified on these instance types. And also, data transfer is critical. You don't want bottleneck to be data, so there includes optimizations for transferring data from your storage to compute. And you want to be able to do this in a cost-effective way. So with Amazon SageMaker, you also get support for managed spot training, which means you can save over 90% training costs. But also for inference, there are a wide range of inference solutions with GPU instances and elastic inference and others we'll talk about. And you can dramatically lower your cost by keeping your performance and your latency budget where it needs to be to deliver a good customer experience. And of course, AWS is framework agnostic, as I mentioned. Bring your favorite framework. They're all supported and first-class citizens on AWS. And with Amazon SageMaker, you can get the benefits of the full stack optimizations, regardless of what framework you're working on. Okay, so before we dive into specific framework level details, I want to share how you can take your framework and run it at scale on Amazon SageMaker. And Amazon SageMaker is purely here to help you, give you a fully managed experience, so you don't have to manage all the infrastructure level services and cluster management services, so you can focus on developing your framework models and algorithms. So let's take a look at how you can run your frameworks on Amazon SageMaker. So there are two ways to do this. The first way is to bring your own training script. So you're developing your training script on your laptop or a desktop. Just bring your own training script and tell SageMaker that you want to run this training script on a cluster of so many GPUs or so many CPUs, and SageMaker will take care of provisioning the cluster, running it, copying your data set from S3, or another storage location and all that. So all the infrastructure stuff is handled for you. Similarly, you may have custom framework extensions or custom framework even, and you may want to bring this even and have SageMaker run it. So in those cases, you can bring your own container. And this is for, again, if you have proprietary code or some custom extensions, then you can have SageMaker run these as well. So the first option with script mode is what we call it, bring your own training script. Here's how it works. So you bring your own training script, and let's say it's called Cypher10, and it's in a source folder with other dependencies. So what you'll have to do as a developer or a data scientist is using the SageMaker SDK, which is free and open source available to you. You can run this anywhere you want, not just on your laptop, desktop, EC2 instances, SageMaker notebooks. Install this and write a TensorFlow estimator where you specify, what kind of framework you want. Here we say this is TensorFlow, but it could be PyTorch or MXNet. And then you can specify the framework version. And this is the interesting part where you specify what type of instance you want to run it on. Say GPU instance, single GPU instance, and how many of them. So one GPU instance. And behind the scenes, everything I'll show you right now behind the scenes, what it'll do is SageMaker will take your training scripts, pull the relevant framework in a container, but you don't have to worry about it. It's happening behind the scenes. And then spin up a cluster for you with a specified number of instances. And then copy your data set from S3 to the cluster, finish training, copy your checkpoints and models back to S3, and tear down the cluster. So everything to the right of this is fully managed for you. Everything to the right of this. So everything to the left of it, this is the only things you have to do, which is to write the estimator function. Pretty cool, in my opinion. It saves you a lot of time. And the experience is very similar with Docker containers. You have a few additional steps because in addition to bringing your script, you also have to build your own container. So similarly, you write an estimator function, specify how many resources you want. Very simple, straightforward. And the difference here is you'll provide a training image name rather than a script because you're bringing your own container. And you build your container and push it to Amazon ECR, Elastic Container Registry, just a place for you to store your container images. And SageMaker will pull that container, provision a cluster, copy your data set from S3, finish training, save results, and all that. All that taken care of for you easily. And all of this is true regardless of what framework you're using. Great. So one of the common questions we get asked is, great, I can do this, but my data set is too large. I have, I don't know, like hundreds of gigabytes or terabytes of data. It doesn't fit in memory. It doesn't fit in disk. How do I train on that? So there are a couple of few different options for you. The first option is for you to use Amazon S3 as your storage location. Let's say you have your data set in Amazon S3. It could be any size you please. If it is moderately sized data set, which is in gigabytes, then you can use an option called file mode. In file mode, SageMaker will fully copy your dataset from S3 into your training cluster you see on the left. If you're doing distributed training or single GPU training, doesn't matter. It'll copy your dataset into the training cluster and then finish training, and fair enough, easy. And if your dataset is large that it doesn't fit on the training instance, what it can do next otherwise is to use something called pipe mode where it will stream the dataset. Now, deep learning is mostly compute bound, not IO bound. So while it is crunching on the current batch, you can have the next batch be transferred automatically for you and made ready before the next batch training starts. Now, if you have a data set in a file storage like EFS because you're using it in other projects and you have teams collaborating in it, you can just mount your file system to Amazon SageMaker training instances. That way your data set never has to leave your file system, and you can have all training instances access data from your file system. At the same time, also collaborate with others in different AWS services that may be consuming the same data set as well. If you really want state-of-the-art performance and the best of the best, what you want to do is use FSx for Lustre file system. And the cool thing about FSx for Lustre, it's designed for high-performance workloads, popular in HPC or high-performance computing workloads. And it fronts an S3 bucket. So your data can still be in S3, and you can still mount it, mount FSX for Lustre as a file system into your training cluster. So you get this fast, high performance um, data read and write, but the data is still backed in S3 and it's synced to S3. So here are different options regardless of whichever framework you're using. You can use one of these three options. And the record setting benchmarks I showed you in the beginning were all done using the third option, which is using FSX for Lustre. Another question we commonly get asked is there's different training instances. How do I choose the right GPU? There are multiple GPUs, right? So there are multiple options. At AWS, we believe it's all about choice. So here's some guidance on how to choose when you have all these choices available. If you're training and prototyping, you should use a P3.2x large, which is a single GPU instance. It gives you a single V100 GPU with 16 GB memory. And this is great for local training, testing, developing, and prototyping. At some point, you want to start running experiments or do small scale distributed training, wherein you want to distribute training to 4 GPUs, or you want to run 4 different experiments in parallel. Then you can try the P3.8x large, which is the same GPUs, but 4 of them. They also include high bandwidth interconnect called NVIDIA's NVLink, which means you can get high inter-GPU communication for distributed training. And as you graduate and do more, you can get a P3.16x large instance where you get 8 of these GPUs for a little more serious experimentation and distributed training. And if you want the state-of-the-art performance is where P3DN 24x large comes into play. And this is a question we commonly get. Wait, you have P3 16x large and 24x large, both have 8 GPUs. What's the difference? But the key difference is with P3DN 24x large, of course, you get a bigger GPU with 32 GB memory, more vCPUs on the instance, much more memory, and faster networking, 100 Gbps bandwidth. And if you really want state-of-the-art performance, this is the instance, and this is popular for distributed training. And all the record-setting benchmarks I showed in the beginning were all done on this instance. So one general recommendation is always start small and add more compute as you go along. Another question we commonly ask is, okay, I've trained my model, I want to deploy it, and what are my deployment options, right? For this is a tricky question because then I would ask you a question back about what's your target SLA? Do you have a latency budget that you want to reach? Is it 10 milliseconds? Is it 100 milliseconds? Your round trip network latency from your customer's mobile app to model inference and back? And are you doing this real time and offline? So there are several different options, and we'll go over each of these. The first is to use a high performance CPU instance. These are great for small models, and your latency budget is not very strict. CPU instances work great. Now, some of these models that you may deploy have maybe mid-sized models, and you want GPU acceleration, but you don't necessarily want to deploy them on a GPU instance, which can be more expensive. But you want enough GPU acceleration so that you can reach your latency budget. In those cases, with elastic inference, you can attach a slice of a GPU to an existing CPU instance over the network. And you can attach different sizes of GPUs over the network. And with this, you can reach your latency budget and still be very cost effective with your model deployment. If you really want the state-of-the-art, lowest latency, high throughput inference, you can host your model on a full GPU instance, such as a P3 or a G4 instance. Especially G4 is a very cost-effective GPU instance for hosting models. And with hosting on a GPU, the advantage is that you get access to CUDA on the GPUs, which means you can write these custom layers for inference. Say it's not part of your framework, then you can actually write very custom code to run there. Whereas in elastic inference, you can't write custom code. You have to use layers that are supported. And finally, if you want the highest performance for the most cost-effective way to do this is using AWS Inferentia. You get really high throughput, and this gives you the best performance per dollar on the cloud right now. And there's a SDK that takes your existing training neural network model from one of the popular frameworks and then deploy it onto an AWS Inferentia or an Inf1 instance. Again, the general guidance here is to always start small, deploy with the CPU instance, and figure out if you want to size up and size up into a more beefier instance, depending on, you're hitting your SLA or whether you're doing real time or batch and so on. Okay, so we've gone through some of the high level things on how to get the most out of your frameworks when you're deploying with SageMaker. SageMaker supports all these different options. It's all about giving you choices so you can choose which is the best approach for you. Now let's take a look at some of the benefits of each of these individual frameworks. Let's starting with TensorFlow. Now, AWS optimizations I mentioned for compute, networking, storage, and all of them are included in the AWS optimizations, which are available either as a deep learning AMI that you can spin up on any EC2 instance, or deep learning container that you can run on SageMaker or Kubernetes or other such service. And these are offered to you free of charge. You just pull the right container with the right version and run them. Now, specifically with SageMaker, you get additional benefits such as built-in support for managed spot training, automatic backup of TensorBoard logs to S3, so you can pull up dashboards, you can do local mode testing, hyperparameter tuning. We'll take a look at a demo of some of these things, and elastic inference where you can deploy, one-click deploy we call it, with a single line of code, you can deploy a secure, highly scalable endpoint. And doing distributed training is super easy. You just specify a number of GPUs and automatically do distributed training. So with that, let's take a look at a quick demo of how you can do this with SageMaker. So if you're new to Amazon SageMaker, if you head over to the Amazon SageMaker console, you'll see something like this. As I mentioned, SageMaker is a high-level ML service which offers fully managed capabilities for labeling, notebook instances, training, managed training, inference, and many other things. I will focus on a couple of subset of capabilities here. And first thing I want to talk about is Amazon SageMaker Studio, which is a brand new capability recently released. And if you're familiar with SageMaker, or you've been using SageMaker in the past and are familiar with SageMaker notebook instances, what you got in the past was a fully managed Jupyter notebook instance backed by a specific instance type you see here. With SageMaker Studio, you get Studio notebooks where you can switch out the compute backend, and here's what it looks like. So the advantage of Studio now is that it's not backed by a single specific instance type that you choose ahead of time. You can actually switch between these instance types automatically. You can switch between different environments, and basically gives you a very nice fluid experience, so you can switch backends and try different things. So this is what the Studio interface looks like. If you're familiar with Jupyter notebooks, this should feel very familiar to you. In addition to some of the standard Jupyter notebook capabilities, you get additional things like experiment tracking, where you can manage experiments. You can look at deployed models here, some of these models that are in service. So there are additional capabilities that are available to you baked into this, so you don't have to ever leave this in order to take a look at progress or other things. Everything you can do right here. So in this demo, we'll do a couple of things. We'll first train a model on a single GPU, and I'll show you how you can host a model. And then I'll talk about how you can scale with almost no code changes, and also run hyperparameter optimizations on 16 GPUs, but just by changing a variable, you can run it on a lot more. So all your training scripts are here on the left. Yeah, I have my training scripts here and some requirements and dependencies. So in order to run training, first what I'll do is I'll upload the dataset to Amazon S3. You may already have your dataset in S3, in which case you'll skip this step. I'll get the path to the location in S3. But the interesting part comes here. Now, managing machine learning experiments is hard. With SageMaker experiments, what I'm doing here is creating an experiment and providing it with a name. The advantage is now I can track all the trials within this experiment, so they're all in one place rather than things all around the place. And this is where I'm creating a trial and I'm providing a name. Now everything under this trial will be under one experiment trial, and I'll show you what that looks like. But this is where the magic happens. So with just this much of code, what I'm able to do here is specify that these are my hyperparameters. And this is my estimator function where I specify my training script and dependencies, how many training instances, what type of instance type, and few other things. And I say estimator.fit, and behind the scenes it'll go spin up an instance, finish training, and provide the results. That's it. If you change the number of instances, you can run it on a lot more GPUs. Deploying is just as easy. I take the estimator function and say deploy and specify an instance type. And I can also specify that I want to run an elastic inference, and all that is taken care of for you. And there's some links to some blog posts that I've written where we go into detail about how to do this. I'll share these resources at the end of the presentation. Distributed training is just as easy. In this case, I'm going to train this on 8 GPU instance, but 2 of them, so total of 16 GPUs. The only changes you have to make is specify that you need to do distributed training, and you'll see here that I specify those distribution parameters right within the estimator function, and that's it. Everything else is taken care of for you, spinning up 2 instances with 8 GPUs and training and all that. And finally, hyperparameter optimizations is where you specify ranges of hyperparameters rather than specific values. So you see here I'm specifying ranges for epochs and learning rate and all that. And similarly, I provide this to an estimator function and hyperparameter tuner, and it'll automatically train these for you. Now, everything you do here can also be seen on the Sagemaker console. So if you head over to Sagemaker console under training jobs here, you'll see that all your jobs are listed here. And you can also take a look at what these jobs look like by clicking on it. And similarly, you can look at progress and all that. The hyperparameter tuning jobs are interesting. Here's a hyperparameter tuning job I just ran. And here, you can take a look at all these tuning jobs that it ran. I can sort these by best model to the worst model. You see one of the best models here is 80% accuracy, worst one with 37% accuracy. And with the best training job here, I'd see this is my best training job. So the one which got 80% accuracy, and the hyperparameters that are right below here. Fantastic. So that's a quick demo that of how to bring. I showed TensorFlow, but if you're using PyTorch or something else, it would be the same. MXNet would be the same approach. So moving on to PyTorch, specifically, again, you get the same optimizations I mentioned. You get the same benefits of running on SageMaker. Couple of things I want to point out is AWS partner with Facebook to also develop TorchServe, which is a model serving framework for PyTorch, similar to how you have TensorFlow serving to TensorFlow, and also Torch Elastic, which is a distributed serving framework for PyTorch. And TorchServe specifically has many cool benefits, such as you don't have to write handlers if you're deploying popular models. No more writing pre-processing and post-processing steps. Simply provide your script either in Torch script or in eager mode, and it'll automatically deploy this model for you. You can deploy multiple models, do A/B testing. We have a blog post where we talk about this in detail, and collaboratively developed by AWS and Facebook. And let's move on to MXNet. And again, same optimizations, and the demo I showed you will work with all these frameworks. They're also available to you, all the optimizations as part of containers and AMI, all the other benefits. The unique thing about MXNet is it has language bindings for a number of languages, such as Scala, Julia, Clojure, and Perl, which you may not find with other frameworks. So, and the another benefit of MXNet is, of course, you have multiple packages that are domain specific. And with Glow-on-CV, you get computer vision specific packages with multiple pre-trained models, with Glow-on-NLP for natural language processing and Glow-TS for time series. And the recent addition to the Glow-on family is AutoGlow-on, which gives you AutoML capabilities with just 3 lines of code. You just specify your data set, you specify a fit function, and you predict. You get state-of-the-art results in many data science competition with winning benchmarks, and the blog post listed there goes into detail. With Glow-on, you get over 200 pre-trained models, so it's super easy to get started, even if you're new to deep learning. And with that, let's recap what we discussed so far. I spoke about deep learning being a challenge with many different model and architectures. These frameworks provide you with convenient high-level abstractions, especially with high-level APIs like Gluon and Keras. You get a lot of pre-trained models that you can get started quickly. And just getting started is one thing. You want to be able to run this in a performant manner. This is where ML services like SageMaker will give you full stack optimizations. So you don't have to worry about infrastructure level optimizations or managing clusters and others. You simply bring in your framework and code, and you can be guaranteed that you'll get the best performance for similar to those record setting benchmarks that I showed earlier. And finally, deploying and hosting your models is super easy, and you have a range of hardware options for deployment. CPUs, Elastic Inference, GPU instances, AWS Inferentia. There's something for you depending on your specific needs here. And finally, I want to share some quick resources with documentations. These are available to you after the presentation. They're dedicated pages for each framework and a link to each of them, so you can check them out for the latest and greatest. Here's some personal resources that I've authored on debugging your models, distributed training, and also a couple of webinars that I've run. And there's, of course, you're not alone in this. There's training resources. Many of these trainings are free. Head over to aws.training/ml and take advantage of these trainings. You can also do in-person training if you're interested. With that, I want to thank you for listening to my talk. I hope you found it useful. If you have questions, today, tomorrow, a week from now, a month from now, don't hesitate to reach out to me. My Twitter and LinkedIn information is here. I also blog on Medium. So with that, I want to say thank you again and have a nice rest of the summit.